This video is on roots of polynomial equations. Recall that one way to find the zeros of a polynomial function is by factoring. However, factoring a polynomial p of x and solving the related equation p of x equals 0 can be difficult, especially if the leading coefficient and the constant term have many factors. You can minimize the number of values that you have to guess and check by using the rational root theorem. The rational root theorem says that a polynomial has possible rational roots at p divided by q, where p is a factor of the constant term and q is a factor of the leading coefficient. What the rational root theorem can do for you is give you kind of a pool of possible factors that you can check, or possible roots that you can check. So let's take a look at an example here. We need to list all of the possible rational roots of x cubed minus 5x squared minus 2x plus 10 equals 0, then find any actual roots. So recall that p is going to be all of the factors of the constant term. So p is going to be the factors of 10. And the factors of 10 are positive or negative 1, positive or negative 2, positive or negative 5, and positive or negative 10. So there's actually 8 possible factors. Q is going to be the factors of the leading coefficient. Or the leading coefficient in this case is 1, which is really nice because there are only 2 factors of 1, and that would be a positive or negative 1. So P over Q, P divided by Q, this is actually pretty easy since my denominator is going to be a positive or a negative 1, are going to be positive or negative 1, positive or negative 2, positive or negative 5, and positive or negative 10. So there are 8 possible rational roots of this equation. Now, I could plug each one of those in, use synthetic division. In fact, that's kind of what you would have to do if your teacher says you can't use a calculator. But I'm going to go ahead and graph this and use my calculator. So, on my HP Prime, go into the function app, and I've already put that function into f1 of x. And I'm going to go to number here to give me a table of values, and I'm going to try each one of those numbers in there. Now, your calculator may not look like this. What I did was I went ahead and changed the setup. So I did Shift Num to get to the setup menu, and when it said number type here, instead of it being automatic, I chose build your own. That's going to allow me to put in the values of x that I want. So I'm just going to check each one of those possible rational roots and see if I end up with a 0 for my f of x. So when I put in 1, I get that f of x is 4. That's not going to work. Negative 1, no. 2, no. Negative 2, no. 5, yes. So when x is 5, f of x or y is 0, so that's one of my possible roots. Let's try the others. Negative 5, no. 10, nope, and negative 10. Oops, enter. No, definitely not. Okay, so that means that I have an actual rational root at x equals 5. And in fact, let's go back to the calculator. I can confirm this with the calculator if I go to plot, and I can see what a graph of this function looks like, and I can see that I do have 3 real zeros, and notice that this one is between negative 2 and negative 1, so that's probably not, that's not going to be a rational number. Between 1 and 2, positive 1 and positive 2, that's not going to be a rational number, and here is my rational 0 at x equals 5. If you can find one root, then you can use synthetic division to factor the polynomial and find the other roots. So here's an example. What are the rational roots of x cubed minus 2x squared minus 5x plus 6? So my factors, my values of p are going to be the factors of my constant term, which is 6, which are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. My values of q are going to be my factors of the leading coefficient, which is 1, which is plus or minus 1. So my possible rational roots, my p divided by q, are going to be positive or negative 1, positive or negative 2, positive or negative 3, and positive or negative 6. Always easy to start with 1, and actually I went ahead and I tried 1, and 1 is one of the rational roots. So I know that one of my rational roots is x equals 1. So I'm going to use that in synthetic division with my polynomial here. So my coefficients are 1, negative 2, negative 5, and 6. Bring down my leading coefficient. 1 times 1 is 1. Add those. 1 times negative 1 is negative 1. Add those. 1 times negative 6 is negative 6. That gives me a remainder of 0. So that means that this turns into x squared minus x minus 6. And that, when that is equal to 0, that factors into x minus 3 and x plus 2. So that means that I'm going to have additional zeros at x equals 3 and x equals negative 2. Now, I could have continued trying all of my possible values of p over q, but if you can find 1, then do synthetic division, and it's possible that this can be factored, or you could use the quadratic formula on it to find, well, that wouldn't give you necessarily give you rational zeros, but if it's factorable, then you will get rational zeros here. A complex number in the form a plus bi, or an irrational number in the form a plus the square root of b, can also be the root of a polynomial equation. Now, these are not going to be rational numbers because a complex number is imaginary, and obviously if it has a square root, for example, square root of 2 or square root of 3, that's going to give you an irrational number, but these can also be roots of polynomial equations. However, they must appear in conjugate pairs. So for example, if you have an a plus bi, you must also have an a minus bi. Or if there's an a plus the square root of b, you must also have an a minus the square root of b. The conjugate root theorem says that if a plus bi is a root of the polynomial p of x, then a minus bi is also a root. And if a plus the square root of b is a root of the polynomial p of x, then a minus the square root of b is also going to be a root. So let's take a look at our last example here. We need to write a polynomial function with rational coefficients so that p of x equals 0 has roots 1, 3, and 1 plus 2i. So I know that I'm going to have 1 root is equal to 1, 1 root is equal to 3, 1 root is equal to 1 plus 2i, and I know that those must appear in conjugate pairs, so I know I have to have another root that's going to equal 1 minus 2i. Now, let's set each one of these equal to 0 to get our factors. So x minus 1, x minus 3, and x minus 1 minus 2i, and x minus 1 plus 2i. So my polynomial, p of x, is going to equal x minus 1 times x minus 3 times x minus 1 minus 2i times x minus 1 plus 2i. Okay, so there it is in factored form, but I need to write it in standard form with rational coefficients, so that means I have a lot of multiplying to do. Let's start with the easy part right here. Let's multiply these two binomials together. Definitely don't multiply two factors, one that has an I and one that doesn't. Multiply your two that don't have the I or square root, and then the two that have the I or the square root in them. So this is going to give me the trinomial x squared minus 4x plus 3. And now I need to multiply this. And this is going to get a little messy, but we can do this. So I'm going to, if you prefer doing like an area model where you would do a box, you're welcome to do that. I kind of like the distributive property. So I'm going to multiply x times each term in the second expression here. So x squared minus x plus 2ix. And then negative 1 times each of those. And I'm going to try to keep them lined up to make adding a little easier. So negative 1 times x, negative 1 times negative 1, and negative 1 times 2i, and then negative 2i times each one of those. So negative 2ix, oops, hold on, I'm going to put that in the third column, third row here. Then negative 2i times negative 1, and then negative 2i times a positive 2i, that's going to give me a negative 4i squared. Let's add those up. Now notice the cool thing here is that all of these i's are going to disappear. Those cancel out, and this right here, remember that I squared is a negative 1. This turns into a positive 4. So I get x squared minus 2x plus 1 plus 4 is plus 5. So this is equal to x squared minus 4x plus 3, which is my first two factors, times x squared minus 2x plus 5. And again, that's going to be just some more multiplying. I'm going to cut to the chase here and say that this ends up being p of x is equal to x to the 4th minus 6x cubed plus 16x squared minus 26x plus 15. And I just didn't take the time to multiply that out for you, but you should know how to do that. So there is a polynomial with rational coefficients that has roots of 1, 3, and 1 plus or minus 2i. So in this video, we took a look at the roots of polynomial equations, how to use the rational root theorem to find the possible factors, and then how to use synthetic division once you find one rational root, how to use synthetic division to find other roots. And then we talked about conjugate pairs of roots that contain imaginary numbers or irrational numbers.